So let's come to the next talk. It's a pleasure for me to announce this. So Roger Dingledine will talk about HOP. We'll talk about the... So, once again, Roger will talk about the Tor project. He is the project leader of Tor, and I'm pretty sure most of you have tried Tor already and might have recognized it's sometimes a little bit slow. And Roger will talk about this now. Thanks a lot.
Okay, hi everybody. I'm Roger Dingledine, the project leader for Tor, and today we're going to talk a little bit about problems that we've encountered when trying to build Tor and make it scale better. Can you all hear me just fine? Great. Okay, so there are a lot of things we could talk about. I'm going to give you a very brief crash course on how Tor works and who uses it, and then we're going to get into the performance issues and architecture problems and so on. So Tor is free software, open source, unencumbered. It comes with a specification and full documentation, RFC style, that describes here's exactly how you can build your own compatible Tor client. And a number of people out there have done that. There's a group in Dresden that built their own Tor client, and another one in Aachen, and a fellow at Yale University built his own. And part of the fun of this is that we actually can describe all the details of what properties we think that Tor gives you. So you can look at it and check for yourself and analyze it, and we tell you as much as we know about how it works. There are about 1,800 volunteer relays all around the world routing traffic for some number of users. It's an anonymity network, so it's a bit hard to tell how many for sure. But I'm figuring more than 100,000, less than 500,000 people are running Tor clients right now. As of the end of 2006, we became a real live 501c3 US nonprofit. We've got 8 full-time people working on developing Tor right now, which is pretty cool. So we started out funded by the Naval Research Lab, part of the US Department of Defense. And from there, we were funded by the Electronic Frontier Foundation. So our claim to fame is that we're the only free software project funded both by the US DoD and the EFF. And from there, we've been funded by Google and a variety of other organizations that care about privacy and freedom around the world, and by NLNet, and perhaps by some people you know. Feel free to get them in touch with me if you know anybody around the world who wants the world to be a safer place. So what do I mean by that? I actually only use the word anonymity when I'm talking to other researchers. When I'm talking to my parents and my grandparents, I tell them I'm working on a privacy system. When I'm talking to Google and Walmart and other companies, I tell them I'm working on communication security or network security. Because anonymity, that's kind of scary, and privacy, who cares about that? But security, good point. I do need that. And when I'm talking to law enforcement and other government groups, I work on traffic analysis resistant communication networks. Because security, they've already got that. There are plenty of snake oil companies around the Capitol that are happy to sell security products. Who cares if they work? And privacy, whatever. Anonymity, okay. But traffic analysis resistance, that's a good point. I really do need that. I want to be able to send my operatives to Israel and not have anybody learn which countries they're talking to. Or I want to be able to investigate this website that some bad people are running without revealing that I'm the one doing it. And then there's a fourth category that we've been learning about recently, which is the reachability side, the blocked users, people in Iran or China or Thailand, or the list goes on and on these days of different countries that are blocking various pieces of the internet. And there are a lot of people, it turns out, once you've built an anonymity system where somebody watching you locally can't figure out which websites you're going to, then that also means that a government locally can't decide which websites you're allowed to reach. It can't block you from getting to CNN because it has no idea which sites you're going to. But that's a separate talk, and you might be able to learn more about that this year in Berlin in December. And in 2 hours, there will be a WikiLeaks panel discussing censorship. So how do you build one of these? The very easy answer is you put a computer somewhere and everybody relays through it. We call it a one-hop proxy. And so Alice 1 asks for some website, and Alice 2 asks for some other website. And that's great, except what happens if there's a central point of failure. That big point in the middle, you can break into the colo and steal the computer. You can put a guy named Guido on an airplane. You can send a subpoena legally or illegally. There are so many different ways to attack a single point of failure. So the goal for Tor is to distribute the trust over multiple hops, so no single relay gets to learn both Alice and Bob. And that means if the first guy is bad, if R1 is trying to figure out what's going on, he can learn that Alice is using Tor, but he doesn't know what she's doing. And if the third one is bad, he knows that somebody is talking to Bob, but he doesn't know who is talking to Bob. And if R1 and R3 collaborate and try to figure it out, then we're screwed. We can't provide everything. But at least it provides a stronger level of security than just the single hop proxy. So far, so good? Okay. And there's crypto, but I'm not going to talk about that today. So we have been trying to figure out what parts of Tor are slow these days. And here's a graph, courtesy Karsten, so we downloaded a 50 kilobyte file 14,000 times over Tor. And we tried to figure out how long it took each time. And there are a couple of things to point out here. One of them is the median download time. The average time that it takes to fetch the 50 kilobyte file is almost 8 seconds. So I want to download a website. It takes something like 8 seconds for me to actually get the website. So that's the first thing to notice. The second thing to notice is this huge long tail here that there are so many of those connections that take 20 seconds, 30 seconds, something like that. So it's really the variance, the variability of the latency that's a big problem. So let's look at that a little bit differently. So here we're looking at downloading 50 kilobytes or 1 megabyte or 5 megabytes. So the previous graph is this little blotch down here where we have an average of 8 seconds and the first quartile and the third quartile. But when we're looking at the 1 megabyte one, it takes 50 seconds or something on average to fetch a megabyte through Tor. It's not so bad. And then when we're looking up here, 5 megabytes takes 150 seconds to fetch 5 megabytes through Tor. So we've actually got a couple of problems here. First of all, fetching small files through Tor takes too long. Second of all, fetching large files through Tor is surprisingly fast. This is not what we built this thing for. And there are a lot of people using it for bulk transfer at this point, and we'll get to that in a few more slides. So there are a bunch of things that we need to talk about in order to figure out how to fix it. And I've identified 6 main categories here of problems that we need to work on. And I'll walk you through each of them as we get to them. And they're ordered by priority. So if we solve only number 3, 4, and 5, and we don't solve 1 and 2, then we're not really going to see the results of fixing those. So we need to solve the first few in order to be able to solve the rest of them well. Okay, so the first one. Congestion control and flow control aren't really done the way that they should be. So Tor uses TCP between each hop when it's connecting. So you use TCP from Alice to the first hop, TCP from the first hop to the second hop, and so on. And that means that there's one TCP connection between 2 Tor relays. And we multiplex a lot of the circuits, a lot of the connections through that TCP stream when we're connecting from one relay to another. And TCP really wasn't designed for that sort of thing. It's only got one trick when it wants to slow you down. And that trick is, I drop a packet, and hopefully your window goes down, and then you'll start sending less stuff. So the other way to look at that is, if one of those connections is sending too much traffic, then all of them get punished for being too fast, and it's going to slow all of them down. So we need to figure out how to break that up so that we don't have one TCP stream sending all of them, but we have a